For 2 minutes of the time, and without any further ado, I'd like to introduce our first speaker, who is Kozel, who is a man who had many talents, obviously. So among other things, he is a consultant for ALPS Research. But he's also one of the few people I've ever met who sort of continued working on their research after they graduated. And sort of giving an update on what we've been doing since then will be the topic of SOC. And Derek, take it away.
Good. So yes, hello, I'm Derek Kozel, and I'll be talking about the research that I did during my master's, and I've done a bit of work on it since, and this will be a mix of both. And it's on optimizing digital modulation schemes using evolutionary algorithms. A little bit about myself. I got a master's in ECE, so my background is not CS, from Carnegie Mellon. Worked for a couple of companies, and now ALPS Research. And my past research has been largely in the software-defined radio space and low-power embedded systems. And yes, so this original work was done during my master's, and it was published as a paper at GECCO, the Genetic and Evolutionary Computation Conference in 2014, and Irvin Tang was the primary co-author on that. Bobby Anucci and Jason Long were the professors of the evolutionary algorithms course, which we both took. So what is evolutionary computing? It's a subfield of artificial intelligence, and the aspect of it that we used was dealing with optimization. When you have a large problem space that's maybe poorly defined, or very complex, very expensive to search, you can use evolutionary algorithms to stochastically search through this. It's a guided search in this case. It doesn't guarantee an optimal result, but it's generally a lot better than just randomly wandering around. One of the things that I've most enjoyed about it is that if you know very little about the actual problem space, but you can have a decent model of it, you can very quickly gather a pretty intuitive sense of, or unintuitive sometimes, of what the output is. And so this is the basic flow. You initialize a whole bunch of candidate solutions. That becomes your population.
Yes, it is.
Unsurprisingly, we're using the Darwinian evolution metaphor here. So I'll be speaking of populations, parents, children, mutation rates, and such like that. And out of this population, hey, cool. Out of this population, you select some parents, you perform mutation, recombination, create new candidates, and then some of those survivors, and then you pick some of those survivors out of these offspring, go back into the population, and you circulate through. Now, how do you do this survivor selection? Well, you evaluate all of these individuals through some fitness function. How good of a solution is this? And the reason I'm presenting here at the radio conference is we chose to use radio as our simulation packet. And it was great. It was completely plug and play. So this is the same thing, just in pseudocode form, initializing the population. I'll be going through this kind of in more detail in later slides, and we don't have that much time, so I'll just move straight through. This will be posted, and the final slide has a link to a GitHub repository that has all the code, the model, and all this presentation as well. So these are the main components of an evolutionary algorithm. You have the representation. In this case, we're dealing with constellations, modulation constellations. And so we should have I and Q floating point numbers representing each constellation point. So the representation ends up just being a string of these floating point numbers. And that's your DNA for the candidate solution. And we're going to mutate these values and recombine them such that you end up with new candidate constellations. The fitness function, we're using a combination of bit error rate and some fudge factors that help you encourage diversity and prevent the algorithm from cheating too badly. Because it will find all of the corners and holes in your simulation and your assumptions, and it will exploit them ruthlessly. The population, just a whole body of candidate solutions. Parent selection mechanism, we're using a combination of fitness and some elites, and so that, I'll talk about that as it shows up. The variation operators covered in the next few slides, mutation, recombination, and that's basically just, are you mutating one candidate solution to create a child, or are you combining several to create one child candidate? And then how do you pick which ones go on the next generation? And that ends up being one of the big criteria for finding good solutions. So representation, as I said, we just used, you can use bit strings. In this case, we should use an array of floating point numbers. And so that's your genotype. The phenotype is, what does this array of floating points mean? It's a constellation of digital modulation. From digital modulation. Fitness functions. So this is the ideal candidate. You have the entire landscape. We know exactly where the best candidate is. It's at the top of the hill. So this is a 3D representation of fitness over the problem space. Now, that's for a 2D fitness space, even with just ARI 4, ARI 8, ARI 16 constellations. Obviously, you're off in many dimensions, and it doesn't lend itself to presenting. The population, so you have this pool of candidates, and then you can divide them up, because you should have an array of candidates. And there's the reasons why you would want to isolate some of these, or pick them out specially. You might want to preserve the best individual, or you might want to keep a whole bunch of solutions separate and let them evolve off on their own. And then maybe merge them later, so that you get a better search across the problem space. Parenthood is not guaranteed, just like in real life. If you're really, really a terrible candidate, and we have a lot of those, then it's very unlikely to be chosen as a candidate for the next generation, because, hey, we're trying to improve here. And yeah, you create lambda offspring whenever you're dealing with math. You seem to have to throw in a few Greek characters just for credibility. Sorry, I know I'm rolling through this, but the interesting stuff is all towards the end. And the last time I gave this talk, we never got to it. Individuals are chosen to be parents, and this is one example of how you can do that. So rather than simply randomly choosing out candidates, you've done this expensive fitness evaluation. Why would you simply randomly choose them out? So in fitness proportional, you say, hey, you were 20% better than anyone else. We're going to assign a much better chance that you're chosen as a parent in any of these variation operators, either as a mutation candidate or as a recombination. And so with recombination, for instance, you would end up with much more likely choosing 2 of the high fitness constellations, the low bit error constellations. And premature convergence is really a problem. And when I get to displaying the results, you'll see convergence is simply how fast does the candidate diversity, the genetic diversity, converge on a single solution. And in every single instance that we did, it just collapsed extremely quickly. So within 50 generations of this, which is only a few hundred, a few thousand maybe evaluations, they're converging on one candidate that's been chosen. And if you had simply one fitness slope, one globally optimum solution, and no other local peaks, this would be fine. Because, hey, we would have just go climbed up the fitness curve and found the best solution, or right in the neighborhood within the granularity of your simulation. But you're much more likely, and with constellations, you can rotate it. There's a number of equally good candidates. And when you get into higher area constellations, there's all sorts of interesting solutions that emerge. And so that's why it explores one or several of those and then converges on a solution. Ranking selection, it turns out that if you do just purely probability based on fitness, you end up with extremely premature convergence, because you get one good solution and all of a sudden 2-3 generations on, that solution is related to every single individual in the population. So this simply ranks them and then assigns a probability. Again, if you want to run through the math, there's excellent papers, and I'll be around on Friday at the HackFest working on this, because as I get towards the end, you'll see there's a few areas for improvement and extension and I would love to talk with anyone interested. The variation operators. So, as I've said, they can work on different arities. Mutation is simply performing any operation that only takes one parent and produces a child, or two children in some cases. Recombination taking two or more. It's a fairly arbitrary classification, but it's useful for discussing it. So here's an example of mutation. We use bit strings just as a really simple example. And so you traverse your DNA array, your bit array, and you can have a probability of mutation and say, roll a random number. Yes, we will flip this bit. No, we won't. No, we won't. No, we won't. Yes, we will. And this, of course, changes your candidate solution. And this is randomly searching, essentially. You are taking a candidate solution and you're moving forward with some of its attributes, but you could have a really, really good aspect of some problem. It's usually not quite as true in constellations, but for some problem spaces, you might end up flipping the sign bit on your DBM value, and all of a sudden your transmitter's gone from +10 to -10. It's not going to work very well. So there's various extension aspects where you can actually assign individual mutation probabilities to each bit, or even co-evolve, because we have an optimization scheme that's optimized itself. And so that's the entire field, which we explore a little bit. Swapping genes. This can be much more, it's not, again, not very interesting for constellations, because if you swap as a pair, an I and a Q, because you're just swapping constellation point, that's not very, not meaningful. But if you're swapping only I or Q, you might be preserving a good high value or a good value. Because again, we're not making assumptions of what makes a good constellation here. We're letting the algorithm explore that. And there's a whole variety, again, of operations. This field has been around for quite some time, so papers are published every year. Oh, we found a new mutation operator. We found a new recombination idea. If you're using floating points, you should really be using this option. And that's part of why I continue on working with it, because there are so many areas to extend. Recombination, here's just two simple examples. You can cross over between two individuals. And this can be really useful if, for instance, the constellation is figured out and you're working with just an area for, it's figured out two really good points. And another one is figured out two very good points. But both of them have points towards the center that are getting confusion between the symbols. And you do crossover, and all of a sudden you have a great solution. You're taking the best of both and end up with a solution. Uniform, again, just switching back and forth between two candidate solutions. Survivor selection, you grow the population every time you create new children. And just because simulation time is limited and you've already evaluated these candidates, you want to throw most of them out. You want to take the children which are hopefully better and move them forward. So there's a whole bunch of different selection criteria, and I'll be showing two of them in the actual results. And sometimes it's very desirable to preserve elites. We found this great solution randomly in the first generation, the second generation. Let's keep this one around by brute force, and then it gets chosen to contribute genetic material to candidate solutions later on. Initialization. This is an area where we got a little bit wrong on our first attempt. Usually you just generate completely randomly. Now, how do you generate a completely random polar coordinate for a constellation point? Oh, well, you just generate a value between 0 and 1 and 0 and 365, right? Well, if you do that, you end up with the clustering that you see here. So you have a bias in your initialization. And hopefully the algorithm overcomes that anyways. But no, the correct answer is to use the PDF of the actual distribution. And so that's in the paper and in the code. I'm sorry, I forgot to include the equation here. But it's fairly simple, but these kinds of things will catch you out. And determination condition. We only have so many simulation cycles, and I've only got so much time each evening. So let's pick when we're going to finish. And this can be either after a set number of generations, or once you've so many convergence and you're really just looking at hundreds of simulations of essentially the same points. You should probably just call it a day then. Or it could be a set number of evaluations. We're going to do 100,000 evaluations. So that's evolutionary algorithms in a nutshell. And there's a whole bunch of different issues with exploiting problems in your model, as I said, premature convergence, getting stuck on local optimums. And so there's a whole bunch of different methods for dealing with that, and that's what we ended up having to explore. We've all seen PSK Constellations, hopefully. So this is for standard capacity. We're mapping the input bits to INQ points, and we're representing all these INQ points as floating point values in the genotype. Sorry again. I realized when I was putting this talk together, we had actually deleted the constellation, the GNU radio companion for this, and moved to a just pure Python implementation of it, or manual Python rather. And so this was the best picture I had. But I'll be reassembling a nice and pretty one tomorrow with some improvements, hopefully. And we just implemented all the algorithms in Python, and it was really easy to get everything in place. Basic evolutionary strategy. This was the first step that we took. Just generate 20 random constellations, evaluate them, perform the mutation, and create children. Then start going to that loop of reevaluating, selecting survivors, and then going back into the mutation. And so here's some of the parameters. We ran it for 150 generations. Each generation had 140 candidate solutions. So we're talking in the tens of thousands of evaluations. And we used mutation and recombination. And this is what the results look like after all the work. And so you get fitness value, and we're going to use that as our base one here. And again, this is a combination of bit error rate and some other factors to keep points spread apart to prevent the same solution being generated lots and lots of times. So it doesn't map directly to anything meaningful. But you can see at the very, very beginning, you get an extremely quick drop-off in premature convergence. And we should really just stop by about generation 40 because we're not getting any meaningful new results. And that's fairly expected. With some problems, you'll see the convergence much slower because the search space is wider. But especially when you start factoring in noise and other channel conditions, the difference between the two constellation points right next to each other is fairly minimal. And so it probably was improving, but the noise was simply alarming. And this is what the run actually looks like. And I believe it'll repeat, so we'll get it again. But you can see it stabilized extremely quickly. The red points are the highest fitness constellation. And it's stabilized into this little and the axes are misleading because when you put them into the radio, they get normalized. So shouldn't have even included the axes or done the normalization. All right, so we're not getting a repeat. Like flip that happen forwards. You see it spreads out very quickly convergent. That's great. We had premature convergence. Let's see if we can get a better answer. So it's all Darwinian, right? Big Galapagos. You have a whole bunch of different islands, and each population ends up with a little bit of a different genetic path, except when some of the individuals move from island to island. So we can emulate this. We have a number of, we chose 4 different islands. It's a pretty good number, and it's basically analogous to running 4 simultaneous runs of the algorithm, except every epoch, every 10, 15, 25 generations, you say, let's take the 2 best individuals and either copy them or move them on to the next island and see how they compete with whatever evolved there. And so you can have one island searching one set of constellation, one constellation that they've chosen as the optimum, the local optimum, and another one chooses a different local optimum. Move them over. You should use a fitness-based driver, or you're just going to lose out because you only transfer a few individuals, otherwise you're just going to be overwhelmed for the destination. And so we have 4 different islands here. And you can see it still converges very quickly, but you're getting gradual improvements all the way up to generation 80 or so. And the best fitness has dropped. And so you can see also that for the best fitness, they converge very quickly to very similar values. There's no real distinct, you can't really see where the migrations happen here because they did all converge quite quickly. And this is a sign that when we were doing our basic evolutionary strategy, we really could have just thrown down both the generations and the number of individuals and gotten a very quick evaluation. And what this hints to me is that you could do this at runtime on the channel because you need a very, very small number of bits, a very small number of evaluations to tune your constellation to it. And this is definitely something that I'm hoping to explore in fairly good depth. And I've started on that, but don't really have anything meaningful at the moment. With the mean, you can see there was a best value here. And so this, sorry, I should have been clear. This is for a single run. The mean best fitness is, we did this evaluation 50 times, full run 50 times. And that's the mean fitness that we run. The variation is quite small. And this is what that looks like. So you can see each island converging, but not quite as much because every now and then you're getting an injection of new individuals. And we've also increased the mutation rates, so we're exploring more of the space, but it does still converge quite quickly. Every now and then, particularly in this island, you can see a shift as some new candidate solutions come in. So now we've done spatial diversity. We've taken individuals and we've spread them out, and every now and then we share some information. The last approach that we took was age layered. So you're taking these candidate solutions and you divide them up by age. You have all the young candidates, the ones that have only been through 2 or 3 generations. They have them compete, because it's not really fair to have them compete with all those older, experienced candidates. But you take the best of them, and they survive on, and they get to compete later on, and again and again and again. So you're competing with your peers. The solution is competing with their peers here. And you restart the bottom. All the candidate solutions that just wash out don't make it. You have a fresh new crop of solutions that you generate for the next run. And what we ended up using is just powers of 2. So all the age ones compete, all the ones that are at least 2 generations old compete, 4, 8, 16, up to the number of generations. You get a much better graph from this one. And so again, we can see you get premature convergence pretty much, or very, very quick convergence. But it does continually improve as it goes down. And you can see as candidate solutions are improving on each run. So the epoch here is only 5, 6 generations for the top ones. And those get moved down. And there's some discontinuity simply because you are adding, there is a mutation operation between this. And so you do end up with a better, best candidate in between the last evaluation and the next, and now you're moving down. But it's interesting because you do see good, you can sometimes see good candidates being generated in the first generation and sweeping down, and you see a discontinuity as that comes into the evaluation. And this is what this looks like. So we're seeing the generation, the layers in order of age here. So the top one continues having very, very high diversity, exploring new peaks. That gets moved down, and you get convergence. You can see the spread and variation whenever a new generation comes in. And every now and then we'll snap to a new best now solution. So what's actually quite interesting is it basically stabilizes into a bimodal set of candidates here. And so that's really coming towards the end of it. And just about was great. And there's a whole bunch of future extensions, which I definitely plan on exploring more. And I already had a great conversation with somebody here who has volunteered to help me out with some better metrics for how good a candidate is and how you can improve on what's really lacking at the moment is the really solid metrics, taking some of these candidate solutions, running them over the air on much longer evaluations, tens of megabytes, hundreds of megabytes, and seeing whether any of these are actually beating out conventional solutions. In simulation, they do at least seem to be for area 8 and 16 constellations, but we don't know how much that is cheating. Because you look at these constellations, and they're not the ones that are chosen when we're implementing conventional systems. But given that all of this is enabled by a schema that has really big flexibility, we're cautiously interested in seeing what actually happens. And improving the simulation. If we're going to go out over the air, we need to have proper framing. We need to see, if you're getting these high bit error rates, what happens when an entire packet gets thrown out? That's, of course, dramatically going to affect how the fitness evaluates. And more complex channels. We have a little bit of multi-path in some of these simulations, and you can explore them in code. But there's certainly a lot more that we can do in terms of rigorously running these candidates through many values of channel conditions, because it can be exploiting the characteristics of a particular channel, which alone would be interesting. So here's the GitHub link, and it'll be in the presentation when it gets posted. And definitely feel free to email me or find me here if you have any questions or comments, feedback. Thanks.
So while I was hanging up next, we might have time for one question. So was Brandon was first. Where's Chris, by the way?
You talked a little bit about probability distributions and fitness functions, but it wasn't quite clear whether or not these constellations are being found based on just the data that you have to transmit itself, or the channel in which you're going through, or both. Could you talk a little bit about what exactly is going on, what metric in those fitness functions the algorithm are using to come up with the best constellation?
So the core metric is bit error rate. We're shoving about a megabyte of data of bits over a channel, and it's basically a new radio channel model with some added like Gaussian noise. And we tried various levels on various simulation runs, but we didn't stick to one or do a regime of testing across a variety. And that's a big improvement in our use.
So presumably the better you know your channel, the better you can choose the fitness function.
Which would be, yes, which would be a really interesting result, because you could do, runtime configurations every 5 minutes, say we're going to throw a megabyte of data over this link and see if we can tune it a little bit. And that's what we really want to do just over the air.
So can you set up your laptop and maybe we can get through this question while we're doing that?
So I'm wondering if the algorithm we're using is a covariance matrix adaptive evolution strategy or something else, and also wondering whether you've looked at the use of Pareto multi-objective optimization as distinct from collapsing your different fitness objectives into a single scalar fitness function.
So we didn't implement that for any of the 3 core presented here. We did explore the multi-optimization, so where you're taking, you have different metrics for you. It's not just the error rate, but how the various properties are interacting. And we started exploring it, but didn't get into depth on it. And that's something I'd like to both learn a lot more about and try and implement. And part of it was that we didn't identify other good metrics. Get error rates seemed like a really obvious one, because what's important, what's more important than simply getting the bits across in the correct state. But it'd be, one of the things I have on my eye is the transmission rate, the actual symbol rate. So you can slow down, speed up, adapt to channel.
Okay, thanks. I thought you said burrito optimization for a minute. Okay, so thanks again, Derek.